Have you ever wondered, just for a quiet moment, whether the universe ends somewhere? Whether there is a final edge you could reach if you kept going long enough? Well, far beyond the last star you can name and the last galaxy you can imagine. And that's the thing, because every instinct we carry from everyday life tells us that all things must have a boundary, a wall, a place where you stop and turn back. You see, when you look around a room, it has corners. When you walk across a field, it has fences. Even your own life feels as though it moves from a beginning toward an ending. So it feels natural, almost unavoidable, to ask the same question of the cosmos itself. Does space end like a box? Does it fade out like the edge of a photograph? Or is that idea perhaps a misunderstanding born from the limits of human intuition? Well, imagine standing beneath a night sky, feeling the slow rotation of the earth beneath your feet, and realizing that what looks flat and endless is in fact curved, quietly looping back on itself without ever revealing an edge. And that gentle revelation hints at something deeper. The universe may not be a thing sitting inside something else. It may not be a stage with curtains waiting at the sides. Perhaps space itself is the thing, stretching, curving, evolving, without any requirement for an outside or a final border. And that invites a more unsettling, more beautiful thought. If there is no edge, then there is no final place to point to and say, here is the end of reality. There is only continuation, structure, and pattern woven into space-time itself. And I suppose that raises a question not just about physics, but about us. If the universe has no edge, what does that say about our desire for endings, for certainty, for neat conclusions? Well, let's take a breath and gently begin to explore why modern science suggests the cosmos has no edge at all. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. From the very beginning of human awareness, long before equations or observatories or even language precise enough to describe distance, people lifted their eyes toward the night and felt a quiet confusion. You see, the sky does something peculiar to the mind. It feels close, almost intimate, like a ceiling gently arched above the world. The stars appear fixed, embedded in a vast but shallow surface, drifting together as though painted onto a rotating dome. And that's the thing. When reality presents itself as a surface, the mind instinctively asks what lies beyond it. If there is a surface, surely there must be a far side. If there is a dome, then perhaps there is an edge where it meets something else. This idea did not arise from ignorance or superstition alone. It arose from perception. Human vision collapses depth at great distances. Mountains flatten into silhouettes. Clouds appear layered against a blue background. And the stars, unimaginably far away, surrender their depth entirely. To the unaided eye, the universe is two-dimensional. It has left and right, up and down, but almost no sense of near and far. So it was natural, perhaps unavoidable, that early humans imagined the cosmos as a shell, a great enclosing structure surrounding the Earth. From that intuition flowed countless stories and models. In many ancient cultures, the sky was a solid thing, a firmament holding back cosmic waters or divine realms. The stars were lamps or holes or ornaments embedded in that surface, and beyond it, well, beyond it was mystery. The edge of the sky marked the limit of existence itself. Even when myths differed, the underlying assumption was strikingly consistent. The universe was something you were inside, and if you were inside something, it must have a boundary. As observational knowledge grew, these stories slowly transformed into more structured cosmologies. Philosophers and early astronomers imagined nested spheres, transparent and perfect, each one carrying a celestial body, the moon on one sphere, the sun on another, the planets beyond, and finally the fixed stars on the outermost shell. And, what's remarkable is how persuasive this picture was. It explained the regular motions of the heavens. It matched what people saw. The stars truly did seem fixed relative to one another, rotating as a single structure each night. The universe felt finite, orderly, enclosed. But even then, the idea of an edge carried profound implications. Beyond the final sphere, there was either absolute nothingness or something entirely unlike the world below. The edge of the cosmos was not just a physical boundary, but a philosophical one. It marked the end of space, the end of matter, perhaps even the end of causality. And so the question of whether the universe had an edge was never merely technical. It touched on meaning, on existence, on humanity's place within the whole. As centuries passed and astronomical models shifted, the edge did not disappear. It simply moved. When the Earth was no longer placed at the center, when the sun became central instead, the universe expanded in imagination, but not infinitely. It was still a structure with a size. Later, when stars were understood to be suns in their own right, scattered across immense distances, the cosmos grew again. But the intuition remained. There must be a furthest star, a last island of light. Beyond that, emptiness. This way of thinking was reinforced by experience on Earth. Every journey has an end. Every map has a border. Sailors once feared falling off the edge of the world because the world, as they knew it, seemed flat and finite. And although that fear was eventually dispelled, it left behind a deeper habit of thought. When confronted with the unknown, the mind reaches for edges. It wants a stopping point. It wants to know where things finish. Early telescopes, for all their revolutionary power, did little to challenge this habit. They extended the visible universe, revealing moons, nebulae, faint smudges of light that later would be understood as distant galaxies. But each telescope also had a limit. Beyond a certain distance, darkness prevailed, and that darkness was tempting to interpret as a boundary. The universe appeared to fade away, not because it ended, but because our instruments could not gather enough light. Yet to the human mind, absence often feels like finality. There is something deeply psychological at work here. We experience the world from a single vantage point. Vision radiates outward. We stand at the center of our own perceptual universe, and from that center everything appears arranged in layers, like scenery on a stage. The idea that the stage itself might curve or loop or lack an edge entirely feels almost absurd at first. It contradicts every bodily experience we have ever had. Classical physics did not help in this regard. Space and time were treated as rigid and absolute. Space was an empty container, stretching infinitely or perhaps finitely in all directions. Time ticked forward at a constant rate, indifferent to motion or gravity. In such a framework, asking about the edge of the universe was not only sensible, it was inevitable. If space is a container, then containers have dimensions. They have limits. They have walls, even if those walls are unimaginably far away. But cracks slowly began to appear. Astronomers noticed that the universe looked roughly the same in every direction. There was no obvious center, no thinning of stars toward some cosmic boundary. Wherever you looked, the distribution of galaxies appeared statistically similar. And that raised a quiet but troubling question. If the universe had an edge, why did it not reveal itself through asymmetry? Why did we not see a direction where matter ran out, where structure gave way to emptiness? Still, intuition is stubborn. Rather than abandoning the idea of an edge, people adjusted it. Perhaps the edge was simply too far away to detect. Perhaps we lived comfortably in the interior, far from the cosmic walls. Or perhaps the universe was expanding, with the edge racing outward faster than we could ever reach it. These ideas preserve the familiar notion of a boundary while accommodating new observations. And that's the thing. Much of the history of cosmology is not a straight march toward truth, but a gradual loosening of assumptions. Each generation inherits metaphors from the last. The universe as a sphere, the universe as a bubble, the universe as a box filled with galaxies. These metaphors are helpful, but they also constrain imagination. They smuggle in the idea of an outside, of something beyond the universe into which it might extend. But what if that assumption itself is wrong? What if the universe is not an object sitting inside a larger space? What if it is not embedded in anything at all? That thought is unsettling because it removes the reference frame we are used to. It asks us to imagine space without an external backdrop, geometry without a surrounding emptiness. There are hints of this in everyday experience, if you look carefully. Directions only make sense within a given context. North and south are defined on the surface of the Earth. At the North Pole, the concept of north dissolves. There is no place further north to go, not because there is a wall, but because the geometry itself does not allow it. And perhaps, just perhaps, the universe behaves in a similar way. The difficulty is that we are trying to visualize something that cannot be easily visualized. We evolved to navigate landscapes, not spacetime. Our brains are exquisitely tuned to three-dimensional objects with edges and surfaces. So when confronted with a reality that may be curved in higher dimensions or governed by unfamiliar geometry, we default to what we know. We imagine walls where there may be none. As scientific thinking matured, especially with the growing precision of astronomical data, it became increasingly clear that the old picture of space as a passive stage was inadequate. Light did not behave as expected. Gravity seemed less like a force pulling across emptiness and more like a property of space itself. The universe was not static. It was changing, stretching, evolving. And if space could change, if it could expand or warp, then perhaps it was not a container after all. And, this realization did not immediately erase the idea of an edge, but it weakened it. The question subtly shifted. Instead of asking where the edge is, scientists began to ask whether the concept even applies. Does it make sense to speak of a boundary if there is no outside? Can there be an edge to something that includes all space by definition? This was a profound shift, not just scientifically, but philosophically. It required letting go of deeply ingrained intuitions. It required accepting that the universe might not conform to the mental images we find comforting, that it might be finite without being bounded, structured without being enclosed. By the time modern cosmology began to take shape, the old question of the universe's edge had transformed into something far subtler. The problem was no longer observational alone. It was conceptual. The universe was revealing itself not as a thing with walls, but as a geometry with rules, a fabric whose properties determine how distances behave, how paths unfold, how light travels. And so, as we stand at this point in the story, it becomes clear that the ancient idea of a cosmic edge arose not from foolishness, but from perfectly reasonable attempts to interpret limited information through familiar metaphors. To move beyond it, we must be willing to abandon the notion of space as flat, passive, and absolute. We must allow for the possibility that space itself can curve, that it can define its own limits without ever producing a boundary you could reach or touch. Once that door is opened, once space is no longer merely the background but an active participant in the universe's behavior, the conversation changes entirely. The idea of an edge begins to dissolve, not because we have found something beyond it, but because we begin to understand that the universe does not require one. And that realization carries us gently, inevitably, toward a deeper exploration of what space truly is, and how its hidden geometry reshapes everything we thought we knew. And once you allow that idea to take hold, once you let go of the comforting image of space as a flat stage stretching endlessly in all directions, something subtle but profound begins to shift in the way the universe feels. Because the next realization is not just that our old metaphors were limited, but that space itself is far more active, more dynamic, and more intimate than we ever imagined. You see, for a very long time, space was treated as nothing more than a backdrop. Matter moved through it. Light crossed it. Events unfolded within it. But space itself was silent, passive, indifferent. It did not bend. It did not respond. It simply was. That picture feels natural because it matches everyday experience. When you walk across a room, the floor does not curve beneath your feet. When you throw a ball, the air does not reshape itself around the motion. Space feels rigid, fixed, reliable. And so, for centuries, science inherited that intuition. Space was assumed to be flat, perfectly flat, the same everywhere. And if space is flat, then geometry behaves exactly as you learned in school. Parallel lines never meet. Straight paths continue forever. And a flat space, well, it invites the idea of edges, of boundaries where the grid might end. But the universe had other plans. Slowly, through careful observation and deep theoretical unease, it became clear that treating space as a passive arena simply did not work. Gravity, in particular, refused to behave. It did not fit neatly into the idea of forces acting across empty space. The way planets moved, the way light bent near massive objects, the way time itself seemed to tick differently depending on motion and gravity, all of it hinted at something far stranger. And this is where the story takes a turn that is both deeply scientific and quietly poetic. The radical idea was this: what if gravity is not something happening in space? What if gravity is something happening to space? What if mass and energy do not merely occupy space, but shape it, stretch it, curve it? And once you entertain that possibility, the notion of a flat cosmic stage begins to crumble. Imagine for a moment that space is not rigid but flexible, not like rubber in the everyday sense, but in a deeper geometric way. Distances can change, angles can shift, straight lines can subtly bend, not because a force pushes them, but because the space they move through is itself curved. This is difficult to visualize because we are creatures who live inside the geometry we are trying to understand. Fish do not notice the water. We do not notice space, but its effects are there, quietly shaping the motion of everything. A simple analogy helps, even if it is imperfect. Think of the surface of the Earth. From a local perspective, it feels flat. You can build cities, draw maps, walk in straight lines for miles without sensing any curvature. And yet, we know the Earth is curved. If you travel far enough in what feels like a straight line, you eventually return to your starting point. There is no edge to the surface, no place where the ground suddenly ends. The curvature reveals itself only when you consider the whole. Now here is the subtle but crucial leap. The surface of the Earth is two-dimensional, curved within three-dimensional space. But space itself does not need an external dimension to be curved. Curvature is an intrinsic property of geometry. It can be measured from within, and that means our three-dimensional space, or four-dimensional spacetime, can be curved without being embedded in anything else. There does not need to be an outside. This realization changes everything. Because once space can curve, the idea of an edge becomes optional, not necessary. A curved space can be finite without being bounded. You can have a universe with a limited volume, yet no walls, no borders, no final stopping point. You simply keep going, and the geometry guides you along paths that may eventually loop, diverge, or behave in ways that defy flat intuition. And this is not philosophical speculation. It is grounded in observation. Light does not always travel in perfectly straight lines. Near massive objects, it bends. Time does not pass at the same rate everywhere. Clocks tick differently depending on gravity and motion. These are not errors or illusions. They are measurements. And they tell us that space and time are woven together into something flexible and responsive. Once that becomes clear, the metaphor of space as a stage collapses entirely. A stage does not change shape when an actor walks across it, but space-time does. Matter tells space how to curve, and curved space tells matter how to move. It is a quiet dialogue, ongoing, everywhere in the universe. And here is where the question of edges begins to dissolve in a very natural way. If space is curved, then straight paths may not behave the way we expect. What we think of as straight may, over vast distances, gently arc back on itself. There is no wall required, no barrier, just geometry doing what geometry does. Think again of the Earth. A sailor heading west does not fall off an edge. There is no cliff at the horizon. The horizon exists, but it is not a boundary. It is a limit of perspective, not of geography. And in the same way, the universe may present horizons that feel like edges, but are not. They arise from the behavior of light, from the expansion of space, from the finite age of the cosmos, not from any physical wall. This challenges something very deep in us. We like to imagine space as something we move through, like air or water. But perhaps that is backwards. Perhaps space is not the container, but the relationship between things. Distance is not something laid down in advance. It emerges from the geometry shaped by energy and matter. And, once you see it that way, the question changes again. You no longer ask where the universe ends. You ask how it is shaped. Is it gently curved like a sphere? Is it saddle-shaped? Is it something even stranger, beyond easy visualization? These questions replace the old obsession with edges. And they are not abstract, they can be tested. Curvature leaves fingerprints. It affects how light spreads, how volumes grow with distance, how patterns appear across the sky. What is most astonishing, perhaps, is how ordinary the consequences feel locally. We do not notice curvature in everyday life because the universe is vast, and its curvature, if present, is subtle on small scales. Just as the Earth feels flat beneath your feet, space-time feels flat in your living room. But scale matters. Over cosmic distances, tiny deviations accumulate. Paths that begin parallel may converge or diverge. The rules of Euclidean geometry quietly loosen their grip. And this brings us back to the idea of the universe having no edge. In a flat, infinite space, you might imagine traveling forever without repetition. In a curved space, the story can be very different. You might travel forever and yet encounter no boundary. No sign saying you have reached the end, just an unbroken continuation shaped by geometry. The difficulty, of course, is letting go of the need for an outside. We are used to thinking of curvature as something happening within a larger space, a bent sheet, a curved surface. But space-time does not need a higher dimensional room to bend into. Its curvature is intrinsic. It is defined by how distances behave within it. And that is a profoundly non-intuitive idea. It means the universe is not sitting inside something else. It is not expanding into emptiness. There is no external reference frame, no cosmic container. The universe is all there is, geometrically speaking. Space does not have an address. It does not exist somewhere. It simply exists. And once you accept that, the idea of an edge becomes almost unnecessary. An edge implies a transition from something to something else, from space to non-space, from existence to nothing. But if space itself is the fabric of existence, there is nothing beyond it for an edge to separate. This is where modern physics quietly but firmly parts ways with ancient intuition. The universe is not a stage. It is the play. It is not a box. It is the geometry that defines what distance and direction even mean. And geometry, when freed from flatness, does not require boundaries. There is also a gentle humility in this realization. It reminds us that our instincts evolved for survival on a small planet, not for understanding the architecture of the cosmos. We must be willing to distrust our immediate intuitions when the evidence demands it. And the evidence, whispered through the bending of light and the ticking of clocks, tells us that space is alive with structure. So as we move forward in this exploration, we carry with us a transformed picture. No longer are we searching for walls at the edge of everything. We are learning to listen to geometry, to ask not where the universe ends, but how it connects, how it curves, how it holds itself together without ever needing an outside. And once you take that step, once you accept that space is not a flat stage but a dynamic participant, another question emerges naturally, almost inevitably. If space itself is all there is, if it does not sit within anything else, then what does it even mean to say that the universe is expanding? Expanding into what? And that quiet, unsettling question gently opens the door to the next part of the story, where the very notion of inside and outside begins to fade altogether. And so that question lingers, gently but persistently. If space itself is not a stage, if it does not sit inside anything else, then what do we really mean when we say the universe is expanding? Expanding into what? It sounds, at first, like a contradiction. Expansion, after all, is something we experience every day. A balloon expands into the air around it. A gas fills the container that holds it. Growth seems to require room, an outside space waiting to be occupied. And that's the thing. Our language betrays us. It carries assumptions that no longer apply. For a long time, even scientists struggled with this idea. The discovery that distant galaxies are moving away from us was initially interpreted in the most intuitive way possible. The universe, it was thought, must be exploding outward from some central point, racing into an empty void beyond its original boundaries. In this picture, the universe resembles a cloud of debris from a colossal blast, fragments flying through pre-existing space. And if that were true, then once again, the idea of an edge sneaks back in through the side door. There would be a frontier, a place where the debris thins out, a boundary between something and nothing. But that picture, seductive as it is, turns out to be wrong. The expansion of the universe is not like an explosion. There is no central point, no outer shell, no direction you could point to and say that is where the expansion is happening. Instead, every region of space is stretching. Distances between galaxies grow, not because galaxies are rushing through space, but because the space between them is changing. And, this is one of the most difficult ideas to truly absorb, because it demands that we abandon the notion of space as a static background entirely. Imagine drawing dots on the surface of a balloon. As you inflate it, the dots move away from each other. None of the dots is the center of the expansion. From the perspective of any dot, all the others recede. And yet, crucially, the dots are not moving across the surface. The surface itself is expanding. The balloon does not expand into the surface. The surface expands as a result of the balloon's changing geometry. Now, the universe is not a balloon, and it does not have an exterior rubber skin floating in a room. But the analogy captures something essential. Expansion is an intrinsic change in geometry. It does not require an outside. There is no surrounding emptiness waiting to be filled. Space itself is doing the expanding, and this is where the idea of an edge truly begins to lose its footing. If the universe is not expanding into anything, then there is no place for an edge to form. An edge would require a transition, a boundary between the expanding universe and whatever lies beyond. But if there is no beyond, the question dissolves. This realization forces us to confront another deeply ingrained assumption. We tend to think of the universe as an object, something with a size, something that occupies a volume. But the universe is not an object inside a larger space. It is the totality of space. Asking what it expands into is like asking what is north of the North Pole. The question assumes a framework that no longer applies. What makes this so difficult is that our intuition is built from experiences within space, not experiences of space itself changing. We move through space. We rearrange objects within it, but we do not feel space stretching beneath us. Locally, the expansion of the universe is incredibly gentle. On the scale of galaxies, stars, planets, and people, other forces dominate. Gravity holds structures together. Electromagnetic forces bind atoms. The expansion only reveals itself across vast, intergalactic distances where gravity has loosened its grip. So, from our everyday perspective, it feels absurd to say that space is expanding everywhere, including here. And yet, in a subtle sense, it is. The expansion simply has no noticeable effect on bound systems. It does not tear atoms apart or stretch your body. It quietly reshapes the large-scale structure of the cosmos. Once you accept this, a new picture emerges. The universe is not a thing moving through space. It is a dynamic network of distances evolving over time. Expansion is not motion through an external arena, but a change in the rules that govern how far apart things are. And that has profound implications for the idea of edges. In a universe like this, the absence of an outside is not a philosophical stance. It is a physical necessity. The equations that describe cosmic expansion do not include a term for an external space. They describe how distances within the universe change relative to one another. There is no variable for what lies beyond, because there is nothing beyond for the equations to refer to. Still, the human mind resists. We imagine space like a loaf of bread rising in an oven, swelling outward. But even that metaphor fails if we imagine the oven itself as space. There is no oven. There is only the bread, and the bread is everything. Perhaps a better way to think about it is to focus on relationships rather than locations. In an expanding universe, what changes is not where things are in some absolute sense, but how they are related. The distance between two galaxies increases. The wavelength of light stretches as it travels. Time itself unfolds differently depending on motion and gravity. Space is not a container, but a set of evolving relationships. And once you see the universe that way, the idea of an edge feels almost misplaced. An edge would be a relationship between inside and outside. But if all relationships are internal, if everything that exists is part of the same geometric fabric, then there is no role for an edge to play. This also sheds light on a common confusion. People often hear about the observable universe and imagine it as a bubble with us at the center, surrounded by a vast but finite cosmos beyond. And it is true that there is a limit to what we can observe. Light has had only a finite amount of time to reach us. There are regions so distant that their light has not yet arrived. But that limit is not an edge of space. It is a limit of information, a horizon, not a wall. Beyond that horizon, space continues. Galaxies continue. Physics continues. They are simply causally disconnected from us, at least for now. And that distinction is crucial. A horizon arises because of the finite speed of light and the expansion of space. An edge would be a fundamental termination of reality itself. The universe, as far as we can tell, shows no sign of such a termination. And, there is something quietly humbling about this. It means that the universe does not arrange itself around our capacity to observe it. Reality extends beyond our view, not because it is hidden behind a boundary, but because the structure of spacetime itself limits what can be seen from any given point. The absence of an outside also has implications for how we think about beginnings. If the universe is not expanding into something, then its origin cannot be understood as an explosion into emptiness. The early universe was not a tiny object surrounded by nothing. It was a state of extremely high density and temperature, where the distances between all points were much smaller than they are now. Expansion describes how those distances evolved, not how something emerged into an external void. This reframing helps dissolve another intuitive but misleading picture, the idea that the universe was once smaller and located somewhere. Smaller, yes. Located, no. There was no center, no privileged point. Every location that exists today existed then, just much closer together. The universe did not grow outward from a seed. It unfolded from within itself. And once again, the idea of an edge finds no foothold. There was no initial boundary that later expanded outward. There was simply space, evolving. What makes this story so challenging and so beautiful is that it asks us to rethink the most basic categories of thought, inside and outside, here and there, beginning and beyond. These distinctions serve us well in everyday life, but the universe is under no obligation to conform to them. As we follow this line of reasoning, another subtle realization emerges. If the universe does not sit inside anything, if it does not expand into an external space, then its overall shape becomes a question of internal geometry alone. The cosmos could be shaped in ways that feel profoundly counterintuitive. It could wrap around itself. It could be finite, yet unbounded. It could connect distant regions in unexpected ways. And this is where the story naturally wants to go next. Once we accept that the universe has no outside, that expansion does not require an edge, we are free to ask a deeper and more precise question. Not where does the universe end, but what is its shape? What kind of geometry describes a space that contains everything yet has no boundary? And to explore that, we must venture further into the strange and elegant language of geometry itself, where the idea of a universe without edges is not just possible, but quietly inevitable. And so we arrive at a quieter but deeper question, one that follows almost inevitably from everything we have just allowed ourselves to accept. If the universe does not expand into anything, if it has no outside, then its overall form must be described entirely from within. Its shape cannot be defined by edges or walls, but only by the geometry of space itself. And that's the thing. Geometry, when you let it speak freely, allows possibilities far stranger and far more elegant than our everyday intuition would ever suggest. For most of human history, geometry meant something very simple. It meant flatness. It meant straight lines that extend forever, angles that add up neatly, and shapes that behave exactly as expected. This is the geometry of floors, fields, and star charts, and it works beautifully on small scales. But the universe is under no obligation to remain faithful to the geometry of classrooms and notebooks. When space itself becomes the subject, geometry becomes a living language, capable of describing worlds without edges and spaces that curve back upon themselves. To understand this, it helps to return once more to an analogy that is humble but powerful. Imagine a two-dimensional being living on the surface of the earth. That being can walk forward, turn left or right, and trace paths across the ground. From its perspective, the world feels endless. There is always more land ahead. No matter how far it travels, it never encounters a boundary where the surface stops. And yet the surface is finite. It has a limited area. It wraps around itself. This is the quiet paradox that geometry allows. Finite does not have to mean bounded. Limited does not have to mean enclosed. A space can have a definite size without possessing an edge. Now take that idea and gently lift it into higher dimensions. Our universe, as far as we can tell, may behave in an analogous way. Instead of a two-dimensional surface curved within 3 dimensions, we may inhabit a 3-dimensional space, curved in a way that does not require an external embedding. The curvature is intrinsic. It belongs to the space itself. One of the simplest ways physicists describe such a possibility is through the idea of a closed geometry. In such a universe, if you travel in what feels like a straight line long enough, you may eventually return to your starting point. Not because you turned around, not because you hit a wall, but because the geometry gently guided your path back home. There is no special direction that leads to an edge. All directions are equivalent. All journeys are unbroken. And this is where language begins to strain. We instinctively want to imagine such a universe as a sphere, like a ball floating in space. But that image is misleading. The universe is not a sphere sitting inside a larger room. The geometry is not extrinsic. It does not bulge into anything. It simply is. A better way to think of it is that distances behave differently than they would in a flat space. Triangles may have angles that add up to more than expected. The circumference of a circle may be smaller than you would predict from its radius. These deviations are not errors. They are signatures of curvature. What matters most for our question about edges is this. In a closed geometry, there is no place where space ends. There is no boundary separating existence from non-existence. The universe is complete in itself. Every point is like every other point. There is no center, no rim, no outside. This possibility unsettles us because it challenges the way we think about size. We often equate finiteness with confinement. A finite room has walls. A finite island has shores. But geometry teaches us that this intuition is not universal. The surface of the earth is finite, yet unbounded. And that example alone is enough to show that our instincts are not reliable guides when it comes to the structure of space. Another important distinction quietly enters the conversation here. Boundless does not mean infinite. These two ideas are often confused, but they are not the same. Infinite means without limit in extent. Boundless means without edges. A space can be boundless and finite at the same time, and that distinction turns out to be crucial for understanding the universe. For a long time, people assumed that if the universe had no edge, it must be infinite, stretching on forever in all directions. That is one possibility, but it is not the only one. A closed universe can be finite in volume yet still have no boundary. The geometry itself closes the space, not by erecting walls, but by shaping how distances behave. And this is not just a mathematical curiosity. Geometry determines physics. The shape of space influences how matter moves, how light travels, how volumes grow with distance. In a curved universe, the large-scale distribution of galaxies, the paths of photons, and the evolution of cosmic structures all carry subtle imprints of that curvature. What is remarkable is how difficult it is to detect. On scales accessible to human experience, the universe appears very nearly flat. Straight lines behave as expected. Angles add up properly. But the universe is vast beyond comprehension. Over such enormous distances, even a tiny amount of curvature can have profound consequences. Just as the Earth feels flat when you stand on it, yet reveals its curvature when you circumnavigate it, the universe may hide its true shape until you consider the largest scales imaginable. And here again, the idea of an edge quietly fades. In a curved universe, there is no special place where geometry breaks down, no cliff where space suddenly stops. The absence of an edge is not a mystery to be solved. It is a natural consequence of the geometry. There is something deeply elegant about this. The universe does not need to be protected from an outside by some cosmic barrier. It does not need to be contained. Its completeness arises from its internal structure. Space wraps around itself not physically, but geometrically. And there is also something humbling in realizing how easily our minds reach for edges when geometry offers alternatives. We imagine walls because walls are familiar. But the universe does not share our architectural preferences. Of course, closed geometry is not the only possibility. Space could also be open, extending infinitely without closing back on itself. In such a case, there would still be no edge. Infinity itself has no boundary. You can travel forever without encountering a termination. Again, no walls are required. The universe either closes gracefully or stretches endlessly. In neither case does it demand an edge. What both possibilities share is the absence of a boundary separating the universe from something else. Whether finite or infinite, curved or flat, the universe does not appear to possess a physical edge in the way we instinctively imagine. And that leads to a quiet but profound realization. The question of the universe's edge was never really about distance. It was about geometry. Once geometry is allowed to be curved, once space is no longer forced into a flat mold, the edge dissolves as a meaningful concept. This realization also reframes how we think about exploration. There is no final destination where reality ends, no last coordinate, no cosmic wall to touch. Exploration becomes not a journey toward an edge, but a deepening understanding of structure, of how space connects to itself, of how the universe holds together without boundaries. And yet, even here, geometry alone does not tell the whole story, because there is another layer, subtler and perhaps even stranger, waiting to be explored. Geometry describes local curvature, but the global confirm, the way space connects to itself on the largest scales, involves something called topology. And topology cares less about exact distances and more about connectivity, about loops, about whether paths can wrap around and meet themselves. So as we let the idea of a boundless yet finite universe settle gently into place, another question begins to form. Not just how space is curved, but how it is connected. Could the universe be shaped in ways that allow light to travel around and return from unexpected directions? Could the cosmos be stranger than even curved geometry suggests? And it is toward that deeper, more abstract layer of understanding that our curiosity naturally drifts next, as we prepare to explore what the universe might be made of, not in terms of distance, but in terms of connection itself. And so, guided by geometry and freed from the need for edges, we turn our attention to something astonishingly tangible. Not a theory written only in equations, not an abstraction whispered among mathematicians, but an actual signal that fills the universe, reaching us quietly from every direction. Because if the universe truly has no edge, if space does not end or break or fold into a boundary, then the cosmos itself should have left behind evidence of that fact. And remarkably, it has. You see, there was a time when the universe was so hot and dense that light could not travel freely. Every photon was trapped in a relentless dance with charged particles scattering endlessly, unable to escape. Space was not empty. It was a glowing plasma, opaque and blinding. In that era, there was no such thing as looking far away. Vision, in any meaningful sense, was impossible. The universe was everywhere bright and nowhere transparent. As the universe expanded, as space itself stretched and cooled, this changed. There came a moment when electrons finally settled into stable orbits around nuclei, forming neutral atoms. In that instant, space became transparent. Light was released, and that light, freed from its cosmic cage, began a journey that continues to this very moment. That ancient light is still with us. It has been traveling for almost the entire history of the universe, crossing expanding space, its wavelength stretched gently by the growth of the cosmos itself. Today, it arrives as a faint microwave glow, invisible to our eyes but measurable with exquisite precision. It comes to us not from one place, but from everywhere. And this is the crucial point. It does not arrive preferentially from any direction. It does not cluster toward some cosmic edge. It does not thin out near an imagined boundary. It surrounds us completely. This radiation is not just background noise. It is a map, a snapshot of the universe at a time when it was astonishingly simple. And simplicity, in cosmology, is a gift. Because when the universe was young, it had not yet developed the complex structures that complicate interpretation. There were no galaxies, no stars, no vast voids. There were only tiny variations in density, small ripples imprinted across space itself. And those ripples are preserved in this ancient light. When scientists first measured this radiation, they expected imperfection. They expected irregularity. What they found instead was uniformity so precise it bordered on the miraculous. The temperature of this glow is nearly the same in every direction. Differences exist, but they are extraordinarily small, 1 part in many thousands. And yet, those tiny differences matter enormously. They are the seeds from which all cosmic structure grew. Now here is where the question of edges becomes unavoidable. If the universe had a spatial boundary, if space simply ended somewhere, that fact would leave a mark on this radiation. Light approaching a boundary would behave differently. It might reflect. It might pile up. It might create distortions, asymmetries, or abrupt changes in temperature or polarization. There would be preferred directions in the sky. There would be patterns that break the symmetry. But when we look, we see none of that. Instead, we see a sky that looks statistically the same no matter where we turn. North, south, east, west, up, down. The universe offers no hint of a cosmic wall, no sign of a reflective edge, no abrupt cutoff where space runs out. The ancient light arrives smoothly, evenly, as though space extends uninterrupted far beyond what we can see. And this is not something we say casually. The analysis of this radiation is among the most precise in all of science. Its temperature fluctuations have been mapped across the entire sky, their angular sizes measured, their statistical properties dissected. And again, the conclusion is the same. The universe behaves as though it has no boundary. The small variations that do exist tell a very specific story. They are consistent with quantum fluctuations in the early universe, magnified by expansion and shaped by gravity. They align beautifully with models in which space is continuous and unbounded. They do not align with models that include an edge. If space ended somewhere, we would expect to see its influence at the largest angular scales. We would expect correlations to break down. We would expect anomalies aligned with the boundary. But what we observe instead is coherence, harmony, a pattern that suggests the same physical laws apply everywhere the light has traveled. And remember how far that light has traveled. It did not emerge from a nearby region. It comes from a surface billions of light, years away, in every direction. If the universe had a finite edge beyond that surface, light would have interacted with it over cosmic time. The absence of any such interaction speaks volumes. There is another subtle point here, one that often goes unnoticed. The ancient light we observe does not form a shell around us in space. It forms a shell in time. Wherever you are in the universe, you see this radiation coming from a spherical surface around you, because you are looking back to the same moment in cosmic history. This creates the illusion that we are at the center of a sphere. But that illusion exists for every observer, everywhere. This is not evidence of a spatial boundary. It is evidence of a temporal one, a limit defined by when the universe became transparent, not by where space ends. And that distinction is critical. The observable universe is bounded. It has a horizon. But that horizon is not an edge of space. It is an edge of information. Beyond it, events have not yet had time to influence us. The universe does not stop there. Our knowledge does. This is one of the most profound lessons modern cosmology offers. Not every limit we encounter is a physical boundary. Some limits arise from the structure of space-time itself, from the finite speed of light, from the age of the universe. Confusing these horizons with edges leads us astray. If the universe had an actual edge, the ancient radiation would behave very differently. We would see reflections. We would see standing wave patterns imposed by boundary conditions. We would see distortions in polarization. But careful measurements reveal none of these features. Instead, the data fit remarkably well with a universe that is smooth, continuous, and without spatial termination. And, there is a quiet beauty in this. The universe does not announce its lack of edges with drama. It does not shout. It whispers, through a nearly uniform glow, through subtle fluctuations, through the absence of anomalies where we might have expected them. This light has crossed the universe without ever encountering a wall. It has traveled through expanding space, its wavelength stretched, its energy diluted, but its message preserved. And that message is simple. Space does not end. Of course, skeptics have asked whether an edge could exist beyond what we can observe. Could the universe terminate somewhere far beyond the reach of this ancient light? In principle, perhaps. But science deals in evidence, not in untestable speculation. And within the observable universe, which already spans an almost unimaginable scale, there is no hint of an edge. More importantly, the physics that describes this radiation does not require one. The models that fit the data best are those in which space extends smoothly and uniformly. Adding an edge complicates the picture without improving its explanatory power. And in science, unnecessary complications are treated with suspicion. There is also a philosophical lesson hiding here. The universe does not owe us intuitively satisfying answers. We expect edges because we live among objects. We expect boundaries because we are bounded beings. But the cosmos operates on scales and principles that do not conform to those expectations. The ancient light teaches us humility. It reminds us that reality is larger than our metaphors. And yet, even as this evidence accumulates, even as the case against a cosmic edge grows stronger, curiosity does not rest. Because geometry and early light tell us how space behaves locally and statistically, they do not fully determine how space might connect to itself globally. Could the universe be shaped in ways that allow light to wrap around? Could paths reconnect? Could space be multiply connected without ever forming an edge? These are not questions about curvature alone. They are questions about topology, about the deep connectivity of space. And to explore them, we must move beyond smooth variations in ancient light and into the realm where geometry gives way to structure, where the universe may reveal itself to be not just boundless, but subtly interconnected in ways that defy even our expanded intuition. And so, with the faint glow of the early universe still echoing around us, with no sign of walls or endings written into its oldest light, we find ourselves drawn forward, toward a stranger possibility. That space itself may loop, fold, and reconnect, not by ending, but by being far more intricate than we ever imagined, a possibility that invites us into the next chapter of this quiet cosmic story. And so, with the ancient light of the universe offering no hint of walls or endings, with geometry suggesting a cosmos that is curved yet complete, our attention drifts naturally toward a deeper and subtler layer of understanding. Because even geometry, powerful as it is, does not tell the whole story. Geometry describes how space bends locally, how distances behave, how angles add up. But there is another question lurking beneath it all, quieter, more abstract, and perhaps even more unsettling. Not how space curves, but how it connects. This is where topology enters the conversation. Topology asks questions that feel almost philosophical at first glance. It does not care about exact distances or precise angles. It cares about continuity, about whether paths can loop back on themselves, about whether space is simply connected or woven together in more intricate ways. And when topology is applied to the universe as a whole, something extraordinary happens. The absence of an edge no longer feels merely possible. It begins to feel natural. You see, two spaces can have the same local geometry and yet be globally very different. To someone walking around on a flat surface, a vast, infinite plane, and a large but finite sheet wrapped into a loop might feel identical for a long time. Locally, everything behaves the same. Straight paths look straight, angles look normal, but edge. Space does not terminate. It does not require a boundary. It simply connects to itself in a way that defies everyday intuition. Topology also teaches us something important about why size alone does not determine whether a universe has an edge. A universe can be small and edge-free, or large and edge-free, or infinite and edge-free. The presence or absence of boundaries depends not on extent, but on connectivity. This is a subtle but powerful shift in thinking. For centuries, people imagined the universe as a container whose size determined its nature, but topology invites us to see the universe instead as a network of connections. What matters is not how far you can go, but whether there is a place where space itself breaks. And again, every line of evidence we have suggests that it does not. The search for topological signatures has also reinforced a crucial distinction. The absence of observed loops does not mean the universe must be infinite. It simply means that if it is finite and multi-connected, its characteristic scales are larger than what we can currently probe. The universe may wrap around itself in ways that lie beyond our observational horizon, and that idea carries a quiet philosophical weight. It means the universe may be complete in ways we cannot directly witness. Its global structure may exist beyond our reach, not because it is hidden behind an edge, but because the universe is old and vast and light has only had so much time to travel. Topology also helps us understand why the idea of an edge is so unnatural in modern cosmology. An edge would be a topological feature. It would represent a boundary where space stops. And boundaries impose conditions. They reflect waves. They alter patterns. They leave signatures. And yet, in every observational test we can perform, space behaves as though it has no such feature. There is no sign of boundary conditions imprinted on cosmic radiation, no indication that waves are constrained by walls, no preferred directions, no asymmetries that hint at a cosmic rim. Instead, everything we observe is consistent with space being either infinite or closed in on itself, but in either case, unbounded. And, This is where the story becomes quietly astonishing, because topology allows the universe to be far stranger than our early intuition suggested, without ever invoking an edge. The cosmos can be finite but edgeless, connected but unbounded, complete without being enclosed. It also reframes the idea of exploration in a subtle way. If the universe has no edge, then there is no final frontier in the sense we once imagined. There is no place where explorers reach the end of existence. Exploration becomes an act of discovery, not of reaching a boundary, but of uncovering structure, connection, and pattern. There is something deeply poetic about this. The universe does not end. It connects. But topology is not merely an abstract exercise. It interacts with physics in concrete ways. The way space connects can influence how fields behave, how particles propagate, how quantum states extend across the cosmos. And that means topology is not just about shape. It is about reality at its most fundamental level. As scientists continue to refine their measurements, to map the sky with ever greater precision, they are not just looking for edges, they are listening for echoes, for repetitions, for subtle correlations that might betray the universe's global connectivity. So far, the silence is telling. No echoes have been found. No loops revealed themselves. And that silence reinforces a simple conclusion. The universe does not need an edge to be complete. Its structure, whether simple or intricate, does not terminate. And yet, topology alone does not answer every lingering question. Even in a universe without edges, even in a cosmos that connects gracefully to itself, there remains a limit to what any observer can experience. Not because of boundaries, but because of time, expansion, and the finite speed of light. There are regions that recede from us faster than light can traverse the expanding space between us. There are events that will never influence us, no matter how long we wait, and those limits can feel like edges, even though they are not. So as we stand here, having let go of walls and embraced connectivity, another question begins to surface. If the universe truly has no edge, why can we not reach everything? Why are there regions forever beyond our grasp? And that question draws us gently onward, away from topology, and toward the role of expansion and causality, where the illusion of an edge arises not from the structure of space itself, but from the relentless stretching of the cosmos and the limits it places on what can ever be known. And so we come to a question that feels almost painfully human. If the universe truly has no edge, if space does not end in a wall or a rim or a final boundary, then why does it feel so limited to us? Why can we not simply keep traveling, faster and faster, until we reach everything that exists? Why is there a sense, persistent and unavoidable, that parts of the universe are forever beyond our reach? It is here, you see, that the illusion of an edge is reborn, not from geometry or topology, but from something far more subtle, from time, from motion, from the limits imposed by causality itself. Because even in a universe with no edge, not everything is accessible. At first glance, this seems contradictory. We are used to thinking that if something has no boundary, it must be fully reachable given enough effort. Walk far enough, sail far enough, fly far enough, and eventually you get there. That intuition works beautifully on the surface of the Earth. It fails spectacularly when applied to the cosmos. The reason lies in a fact that is both simple and deeply unsettling. The universe is expanding. And not only expanding, but doing so in a way that changes what it means to travel through space at all. When we say that distant galaxies are receding from us, it is tempting to imagine them flying away like sparks from a firework. But that picture is misleading. Galaxies are not racing through space in the usual sense. Instead, the space between us and them is stretching. And that stretching is relentless. It does not slow down to accommodate travelers. It does not pause to allow light to catch up. It simply continues. This leads to a startling consequence. There are regions of the universe that are moving away from us so quickly, due to the expansion of space itself, that even light emitted from them will never reach us. Not because light is slow, but because space expands faster than light can traverse it. Now, this must be handled carefully, Nothing is locally moving faster than light through space. That would violate the rules of physics. But space itself is not constrained in the same way. The expansion of space can increase distances between objects at an effective rate greater than the speed of light, without breaking any laws. And that distinction is crucial. Imagine trying to walk up a down escalator. You move forward step by step, but the escalator carries you backward. If it moves slowly enough, you make progress. If it moves too quickly, you never reach the top. No matter how long you walk, you remain confined to the lower region. The top exists. It is real. It is simply unreachable. The universe works in a similar way on the largest scales. There is a boundary beyond which events can never influence us. Not because space ends there, but because light from beyond that boundary cannot overcome the expansion of the space in between. This boundary is known as a horizon, and horizons are not edges. They are limits imposed by time and motion. This distinction is subtle but absolutely fundamental. An edge is a place where space stops. A horizon is a place beyond which information cannot reach us. The universe appears to have horizons. It shows no evidence of edges. The observable universe is defined by such a horizon. It encompasses everything from which light has had time to reach us since the universe became transparent. Beyond it, there are galaxies, structures, perhaps entire regions of space that exist just as surely as the ones we see. But they are causally disconnected from us. Their light has not arrived. Their influence cannot reach us. They are not hidden behind a wall. They are separated by the geometry of space-time itself. And this is where intuition rebels, because it feels deeply unfair. If the universe has no edge, why should there be places we can never see? Why should existence be partitioned by something as abstract as causality? But causality is not abstract. It is woven into the structure of space-time. It defines what can influence what. It draws invisible boundaries that are not physical barriers but relational limits. They arise naturally in an expanding universe with a finite age. This also explains why traveling faster does not help. No matter how fast you go, even if you could travel arbitrarily close to the speed of light, you cannot outrun the expansion of space on the largest scales. There are regions that recede faster than any traveler can pursue, not because of motion through space, but because the space itself is stretching. And so, even in a universe with no edge, there are unreachable regions. This is where many people mistakenly imagine that they have found the edge at last. The horizon feels like a boundary. It encloses us. It defines a finite region. It tempts us to think that beyond it, space ends. But that is an illusion born of perspective. Every observer, anywhere in the universe, has their own observable horizon. From their point of view, they are surrounded by a finite sphere of visibility. And yet, every other observer experiences the same thing. There is no special location, no privileged center. The horizon is not a feature of space itself. It is a feature of observation. If the universe had a true edge, there would be something fundamentally different about approaching it. Physical laws would change, geometry would break, signals would behave strangely, but nothing like that is observed. Instead, the laws of physics appear the same everywhere we can measure them, up to the very limits of our observation. The horizon is not a wall. It is a consequence of the universe having a history. And this brings us to another deeply counterintuitive realization. The observable universe is not static. It changes over time. As the universe ages, light from more distant regions has time to reach us, expanding our observable horizon. At the same time, accelerated expansion can push other regions permanently out of reach. Horizons can grow. Horizons can shrink. But edges do not behave this way. An edge would be fixed, absolute, final. A horizon is dynamic. This dynamism reveals something profound about the nature of reality. What exists is not limited by what can be observed. The universe does not wait for us to see it in order to be real. Existence extends beyond observation, bounded not by walls, but by causal structure. And this is where the emotional weight of cosmology often lands. There are parts of the universe that will never be known to us, not because we lack technology or imagination, but because space-time itself forbids the exchange of information. The universe is generous, but it is not obligated to be fully accessible. Yet this limitation should not be mistaken for evidence of an edge. Quite the opposite. It is precisely because space does not end that horizons arise. In a finite box with walls, everything inside is, in principle, reachable. In a boundless expanding universe, limits emerge naturally from the interplay of time, distance, and expansion. And this brings us full circle. The reason we cannot touch an edge, no matter how fast we go, is not because the edge is running away from us. It is because there is no edge to run toward. There are only horizons, shifting and evolving, marking the limits of causal contact. This understanding also clarifies why searching for the edge of the universe is the wrong kind of question. The universe does not end in space, it ends in time, or rather, our access to it does. The question is not where space stops, but which events can influence which others. And that realization opens the door to a new way of thinking about cosmology. Instead of asking about edges, we ask about models, about whether our theories, when simulated and tested, naturally produce a universe that matches what we observe. Do they create horizons rather than walls? Does curvature behave correctly? Do patterns in ancient light emerge naturally? And that shift, from imagining boundaries to testing models, carries us naturally into the next stage of the story. Because once we accept that horizons are not edges, that limits of observation are not limits of existence, we are left with a powerful challenge: to build mathematical universes, to simulate entire cosmologies, and to see whether a universe without edges truly explains the data better than one that insists on walls where none are seen. It is there, in those simulations, that the idea of an edgeless cosmos faces its most rigorous tests, and it is there that the universe once again quietly reveals its preference for continuity over confinement. And so we step into a realm where imagination alone is no longer enough. Having followed the logic of geometry, topology, horizons, and causality, science does something quietly radical. It builds entire universes, not in the heavens, but in equations and simulations. Because if the cosmos truly has no edge, if walls and boundaries are illusions born of intuition rather than reality, then this claim must survive the most unforgiving test of all. It must reproduce the universe we actually observe. You see, modern cosmology does not rely on a single idea or a single line of reasoning. It is a convergence, a meeting place where theory, observation, and computation quietly interrogate one another. And simulations are where that interrogation becomes relentless. They allow us to ask a very precise question. If we assume a universe with no edge, with curved space or complex connectivity, governed by known physical laws, do we recover the cosmos we see when we look up at the sky? The answer, again and again, is yes. These simulations begin with something deceptively simple, an early universe that is almost uniform. Tiny fluctuations in density, a set of physical rules describing gravity, expansion, and the behavior of matter and radiation. From this quiet beginning, the universe is allowed to evolve. Space stretches, matter clumps, light propagates, structures emerge, galaxies form, voids open, filaments weave themselves across vast distances. And all of this unfolds without ever needing to introduce an edge. What is remarkable is how sensitive these simulations are to boundaries. If you impose an artificial edge, even a mathematically subtle one, the universe begins to misbehave. Patterns in the ancient radiation become distorted. Temperature fluctuations no longer match observations. Polarization signals acquire anomalies. Large-scale structures align in unnatural ways. The universe begins to look wrong. And this is crucial. Science does not reject edges because they feel philosophically uncomfortable. It rejects them because they leave fingerprints that do not match reality. In simulations where space is continuous and unbounded, the statistical properties of the universe align beautifully with what we measure. The distribution of galaxies, the scale of cosmic voids, the patterns imprinted in ancient light. all of it emerges naturally, without the need for walls or terminations. But when boundaries are introduced, problems arise. Waves reflect, correlations break symmetry, the universe acquires preferred directions, and none of these features are seen in the real cosmos. This is not a small detail. Boundaries are not neutral additions. They impose conditions. They constrain how fields behave. They alter how waves propagate. In a universe governed by waves at every level, from quantum fluctuations to cosmic radiation, boundaries are loud. They announce themselves. And yet, the universe is quiet. The simulations that best match reality are those in which space either extends indefinitely or closes smoothly upon itself. In both cases, there is no edge, no place where physics must stop and ask what lies beyond. And there is something almost poetic about watching these simulated universes evolve. Starting from a nearly featureless state, they blossom into complexity. Galaxies swirl into existence. Clusters assemble. Vast, empty regions open between filaments of matter. And all of this unfolds as a natural consequence of internal dynamics. No external container required. No boundary conditions imposed by hand. It is here that the absence of an edge becomes not just plausible, but economical. The universe does not need extra assumptions to function. It does not require special rules at a boundary. It simply evolves according to local laws applied everywhere. And that universality is telling. Physical laws appear to be the same wherever we look. There is no sign that they change near some distant rim. No evidence that spacetime behaves differently at large scales. Simulations that assume uniform laws throughout space reproduce observations far better than those that carve the universe into regions with special edges. This is an important philosophical point disguised as a technical one. Nature seems to prefer simplicity. Not simplicity in appearance, but simplicity in principle. The universe behaves as though it does not care about being enclosed. There is another subtle insight that emerges from these simulations. When scientists explore universes with different global shapes, different topologies, different curvatures, they find that many of these possibilities still produce realistic cosmologies. The universe can be finite or infinite. It can be slightly curved or nearly flat. It can connect back on itself in exotic ways. But in all these cases, the absence of an edge is a common thread. Edges are not forbidden. They are simply unnecessary. And unnecessary features are rarely part of nature's design. What simulations also reveal is how misleading our intuition can be about size. A universe can be finite yet unimaginably large, so large that no experiment within it could ever detect its closure. In such a case, the universe would feel infinite to every observer, even though it is not. And yet, even then, there would be no edge. Space would wrap around itself so gently that no traveler would ever encounter a boundary. This aligns beautifully with everything else we have learned. Horizons arise not because space ends, but because time and expansion limit communication. Geometry shapes paths, not walls. Topology defines connectivity, not confinement. And simulations bring all of these ideas together into a single, coherent picture. A universe without edges is not an exotic speculation. It is the default outcome of letting known physics operate freely. This also explains why the search for an edge has quietly faded from serious cosmology. Not because curiosity has diminished, but because the question itself has been transformed. Instead of asking where the universe ends, scientists ask whether a given model reproduces observed data, and models with edges consistently perform worse. Edges introduce asymmetries, they complicate equations, they require justification, and they fail to improve predictions. The cosmos, it seems, has no need for them. There is something deeply humbling in this. The universe does not arrange itself according to the limits of our imagination. It unfolds according to principles that are elegant, consistent, and indifferent to our desire for boundaries. And yet, even as simulations strengthen the case for an edgeless universe, they also reveal something else. There are ingredients in the cosmos whose nature we do not yet fully understand. Forces that shape expansion, energies that permeate space itself, components that influence the fate of the universe on the largest scales. One of these ingredients, quiet yet dominant, plays a particularly important role in reinforcing the absence of edges. It does not clump. It does not form walls. It does not gather at boundaries. Instead, it spreads evenly, accelerating the expansion of space itself. And as simulations incorporate this mysterious component more accurately, the picture becomes even clearer. The universe does not develop edges as it evolves. It becomes smoother, more uniform on the largest scales. Expansion accelerates, horizons shift, but no boundary ever forms. And that realization carries us gently onward. Because to truly understand why the universe remains edgeless as it grows, we must confront the nature of this pervasive influence. This energy that fills space, drives expansion, and quietly ensures that no cosmic wall ever comes into being. To understand the universe without edges, we must understand the force that pushes space apart itself. And it is there, in the strange and subtle role of dark energy, that the next part of the story begins, waiting patiently just beyond the simulations, woven into the very fabric of the expanding cosmos. And so, having watched simulated universes unfold without walls, having seen geometry and topology quietly conspire to remove the need for boundaries, we arrive at a force that seems, at first glance, almost too subtle to matter, and yet turns out to be decisive. A presence that does not clump like matter, does not shine like stars, does not trace filaments or gather into structures, and yet dominates the fate of the cosmos. This is the ingredient that quietly reinforces the story of a universe without edges. Dark energy. To understand why dark energy matters so deeply to this question, we have to pause and let go of another familiar intuition. In everyday life, energy gathers, it pools, it collects in places. Heat flows from hot regions to cold ones. Matter falls inward under gravity, piling up into planets, stars, galaxies. We are used to thinking of influence as something that concentrates, something that builds boundaries and structures. And for most of cosmic history, gravity played that role. It pulled matter together, sculpting the universe into clusters and voids. But dark energy does the opposite. It does not collect. It does not form edges. It does not prefer one place over another. Instead, it appears to be spread smoothly throughout space itself. Every region of space carries it, not attached to matter, not confined to locations, but woven evenly into the fabric of space-time. And that evenness is crucial. If the universe had an edge, if space terminated somewhere, one might reasonably expect dark energy to behave strangely near that termination. Boundaries tend to distort fields. They create gradients. They introduce asymmetries. A container affects what it contains. But observations show no such effect. Dark energy does not pile up at some distant rim. It does not weaken near an imagined boundary. Its influence appears the same everywhere we can measure. Instead of creating edges, dark energy erases them. The most striking evidence for dark energy comes from the discovery that the expansion of the universe is accelerating, not slowing down as one might expect if gravity alone were in charge, but speeding up. Galaxies are not merely drifting apart. The space between them is stretching faster and faster as time goes on. And, this acceleration has profound consequences. In an accelerating universe, the formation of large-scale boundaries becomes even less likely. Structures grow, yes, but the space between structures grows faster still. The universe becomes smoother on the largest scales. Differences are diluted. Inhomogeneities are stretched away. If edges were ever going to form, acceleration works against them. Imagine a universe with a finite boundary. As expansion accelerates, that boundary would represent a discontinuity, a place where the uniform influence of dark energy abruptly stops. That would create observable effects, distortions in expansion rates, anisotropies in large-scale structure, deviations in the behavior of light near the boundary. But no such effects are seen. Instead, the expansion appears remarkably uniform. Everywhere we look, space expands in the same way. Dark energy does not signal an end to space. It treats space as something that continues. This reinforces a theme that has been quietly building throughout our journey. The universe behaves as though it has no special locations, no preferred directions, no distinguished edges. Physical laws apply universally. Dark energy, in particular, seems to embody that universality. It is not tied to galaxies. It does not fade in voids. It does not intensify near clusters. It simply is everywhere the same. And this has a deep implication. If the universe had an edge, that edge would be a special place, a place where something changes, where space ends, where laws might require special conditions. But dark energy shows no sign of respecting such a distinction. It flows, or rather exists, seamlessly across all of space. In simulations that include dark energy, this effect becomes even clearer. As the universe evolves, acceleration smooths out large-scale features. It does not create boundaries. It does not sharpen edges. It does not allow structures to pile up into walls. Instead, it stretches everything apart. Even hypothetical edges become dynamically irrelevant. Any initial irregularity is rapidly diluted. Expansion accelerates away from it. Space becomes more uniform, not less. This is one of the quiet reasons why cosmologists are increasingly confident that the universe has no edge. Not because edges are mathematically impossible, but because the dominant energy component of the universe actively works against their formation and persistence. And there is something almost poetic about that. The force that drives the universe apart also removes the conditions under which a boundary could meaningfully exist. Expansion is not tearing the universe into pieces. It is smoothing it into continuity. Dark energy also sharpens the distinction between horizons and edges. As acceleration increases, horizons become more prominent. Regions of space recede beyond causal contact. Light emitted today from sufficiently distant galaxies will never reach us. The observable universe shrinks in a sense, even as space itself grows. This can feel like the universe is enclosing us, surrounding us with an unreachable boundary. But, again, this is not an edge of space. It is an edge of influence. Dark energy creates horizons, not walls. And that distinction matters deeply. A wall is something you could, in principle, reach. A horizon is something that recedes faster than you can approach. In an accelerating universe, horizons are inevitable. Edges are not. Dark energy ensures that the universe becomes increasingly fragmented into causally disconnected regions. But each region, taken on its own, remains edgeless. Space does not stop at the horizon. It simply becomes inaccessible. This also explains why searching for the edge of the universe becomes less meaningful as our understanding deepens. The universe is not structured like a room. It is structured like an ever-expanding network of regions, each with its own horizon, each experiencing the same underlying laws. And, this realization carries a quiet, emotional weight. It means that much of the universe will forever lie beyond our reach, not hidden behind a boundary, but separated by the relentless stretching of space. There will be galaxies whose light will never touch us, no matter how long we wait. But they do not mark the end of existence. They mark the limits of connection. Dark energy also undermines one final intuitive picture: the idea that if the universe had an edge, expansion might push matter toward it, accumulating material at the boundary like foam at the edge of a wave. But dark energy does not push matter toward anything. It acts uniformly. It accelerates expansion everywhere. There is no preferential direction, no accumulation zone, no cosmic shoreline. Matter does not drift toward a rim. It is carried apart by the growth of space itself. And that uniformity is reflected in observations. We do not see an excess of matter in any direction. We do not see gradients that would suggest a nearby boundary. The large-scale universe looks statistically the same in all directions, consistent with an accelerating, edgeless cosmos. As simulations incorporate dark energy more accurately, the conclusion becomes unavoidable. Universes with edges behave differently. They leave signatures. They introduce anisotropies. They complicate the smooth expansion driven by dark energy. Universes without edges, by contrast, evolve naturally under acceleration, matching what we observe. Dark energy does not require an edge. It does not tolerate one easily either. And yet, even as dark energy strengthens the case for an edgeless universe, it introduces new mysteries. What is this energy? Why does it exist? Why does it have the value it does? Why does it dominate the universe now rather than earlier? These questions remain open, but one thing is clear. Whatever dark energy is, it does not behave like something confined within boundaries. It behaves like a property of space itself. And that is the final, subtle twist. Dark energy suggests that space is not empty. It has structure, it has energy, it has dynamics, and if space itself carries energy, then space is not a container waiting to be filled. It is an active participant in the universe's evolution. Edges belong to containers. A universe where space itself has energy has no need for them. So as we let dark energy take its place in the story, as we watch it smooth, stretch, and accelerate the cosmos, the picture becomes clearer still. The universe is not a thing with a rim. It is a process. A continuous unfolding of space-time shaped by geometry, connectivity, causality, and energy. And yet, even here, at this point of apparent clarity, another question begins to form. Because if space itself is active, if it carries energy and evolves, then perhaps at the deepest level, space is not continuous at all. Perhaps there is a more fundamental structure beneath it. A graininess, a network, a quantum foundation from which geometry itself emerges. To understand whether the universe could have an edge at the most fundamental level, we must descend further, beyond classical geometry, beyond smooth space-time, into the realm where space itself may be quantized. And it is there, at the smallest scales imaginable, that the final arguments against edges begin to take shape, waiting for us in the strange and beautiful territory of quantum space. And so, having followed the universe outward across vast distances and inward through the accelerating expansion of space, we now descend to the smallest scales imaginable, to a realm where even the idea of smooth space begins to dissolve. Because if the universe truly has no edge, not just in practice but in principle, then this absence must persist all the way down to the deepest layer of reality. It must survive not only classical physics, but quantum physics as well. And that is where the story becomes at once more abstract and more profound. At the smallest scales, space does not behave the way we are used to. The smooth fabric described by geometry and relativity begins to fray. Distances lose their certainty. Time itself becomes fuzzy. The comforting picture of space-time as a continuous surface breaks down. And in its place, physicists have begun to glimpse something far stranger. A universe in which space is not fundamental, but emergent. This idea alone changes how we think about edges, because edges belong to continuous objects. They are defined by surfaces, by terminations, by places where something ends and something else begins. But if space itself is not continuous, if it is built from discrete elements or relations, then the very notion of an edge becomes suspect. What would it even mean for a network to have a boundary when the network is all there is? In several approaches to quantum gravity, space is not treated as a smooth background at all. Instead, it is described as a web of relationships, nodes connected by links, interactions rather than locations. Geometry emerges from how these elements connect, not from an underlying grid. In such pictures, space resembles a network more than a surface, and networks do not end the way surfaces do. They can be finite without having boundaries. They can loop, reconnect, and close upon themselves. Their structure is defined internally, not by an external frame. One striking implication of this is that the idea of an edge may be a purely classical artifact, a convenient approximation that arises when space is treated as continuous and extended, but which disappears when we examine the universe at its most fundamental level. At those scales, the question is no longer where space ends, but how it is assembled. And this is where a quiet philosophical shift occurs. we stop asking about borders and start asking about processes. How does space emerge from something deeper? How do distances arise from relationships? How does geometry come into being at all? In many quantum gravity models, there is no room for an edge because there is no container. There is no background space in which the universe sits. The universe is not embedded in anything else. It is self-contained at the most fundamental level. If there were an edge, it would have to be encoded in the fundamental rules. It would have to appear as a special termination in the underlying structure. But introducing such a termination creates problems. It breaks symmetry. It requires special conditions. It demands an explanation for why the universe should end there and not somewhere else. Nature, it seems, avoids such special pleading. Instead, the emerging picture is one in which space is relational. Points do not exist independently. Distances are not pre-given. They arise from interactions. And in such a framework, an edge would not be a physical object. It would be a failure of connection, a place where relationships simply stop. But no evidence suggests that reality is built this way. Quantum theories of space tend to favor completeness. Networks close. Structures are self-consistent. There is no dangling end where the universe simply runs out of rules. And this resonates with everything we have already seen at larger scales. Geometry removes the need for edges. Topology removes the need for boundaries. Expansion creates horizons, not walls. Dark energy smooths the universe rather than carving it. And now, at the deepest level, quantum structure removes the very stage on which an edge could exist. Edges, it seems, are an invention of approximation. Another important insight emerges here. In classical thinking, an edge is something you could approach, something that exists at a location. But in quantum gravity, location itself is not fundamental. It is an emergent concept. Asking where an edge is becomes meaningless when there is no underlying coordinate system in which to place it. And this is deeply counterintuitive, because our entire experience is built on location. Here and there, near and far. But the universe does not owe us an intuitive foundation. It owes us consistency. At the smallest scales, consistency appears to demand that space has no boundary, that the rules apply everywhere they apply at all, that there is no final layer where physics simply stops. Even the concept of the smallest possible length reinforces this idea. If there is a minimum scale below which space cannot be divided, then there is no way to approach an edge continuously. There is no infinite sequence of steps leading to a boundary. The notion of an edge dissolves into discreteness. And this brings us to a remarkable realization. The absence of an edge is not merely a large-scale feature of the universe. It is a property that appears to be woven into reality at every level. From the cosmic web to quantum networks, the universe resists termination. This does not mean the universe is infinite in every sense. It may be finite in content, finite in information, finite in volume. But finiteness does not require a boundary. Quantum space can be finite and complete without ever ending. And that challenges one of our deepest intuitions. We associate finitude with enclosure, with walls, with edges. But the universe consistently demonstrates that this association is not necessary. In quantum gravity, boundaries are often introduced only as mathematical tools, as conveniences for calculation, as artificial cutoffs. And when they are introduced, they are carefully distinguished from physical reality. They are boundaries of description, not boundaries of existence. And that distinction matters. Because when physicists talk about edges in these contexts, they are not talking about the universe running out. They are talking about the limits of a model. The edges belong to our equations, not to the cosmos. This reinforces a theme that has echoed quietly throughout our journey. Every time we thought we found an edge, it turned out to be a limit of perspective, a horizon, a boundary of observation, a boundary of approximation, never a boundary of reality itself. And there is something profoundly humbling in that. It suggests that the universe is not built around our conceptual comfort, it is built around coherence. Quantum space, strange and elusive as it is, appears to honor the same principle. There is no preferred place where the rules break. no final surface where structure gives way to nothing. Reality is stitched together without seams, and yet even here questions remain. If space emerges from quantum structure, what determines its global form? How does a universe that is fundamentally discrete give rise to smooth geometry? How do finite structures appear infinite? How does something without edges feel endless? These questions lead naturally to a final conceptual hurdle: the apparent contradiction between being finite and having no boundary, a contradiction that haunted thinkers for centuries and still unsettles us today. If the universe can be finite yet edgeless, does that violate logic? Does it undermine our understanding of space? Or does it simply reveal the limits of intuition once again? To answer that, we must confront the paradox head-on. We must examine how something can be complete without being enclosed, how wholeness does not require walls, and how the universe, in its quiet consistency, invites us to accept a form of completeness that feels unfamiliar, but is no less real. And so, having descended to the quantum roots of space, having seen edges dissolve even at the deepest level, we are ready to face the final conceptual tension: the idea that a universe can be finite, entire, and yet never end. A thought that seems contradictory until, at last, it is not. And so we stand at what feels like a contradiction, a conceptual knot that has troubled human thought for as long as we have tried to imagine the whole of reality at once. How can something be finite and yet have no edge? How can a universe contain a limited amount of space, a definite volume, and still offer no wall, no boundary, no final surface where existence stops? It sounds impossible, almost like a trick of words. And that's the thing. It only sounds impossible because our intuition has been trained by rooms, boxes, islands, and containers. The universe, once again, is under no obligation to resemble our furniture. To feel the tension properly, let's slow down. Finite in everyday language means limited. It suggests counting, measuring, a sense that if you kept going, you would eventually run out. And edge, likewise, feels inseparable from that idea. If something is limited, surely there must be a place where it ends, a last step, a final boundary, a corner, a wall. But geometry has already begun to loosen that bond for us. And now, at this stage of the story, we can finally face the paradox directly, not as a problem to be dismissed, but as a doorway to a deeper understanding of what space actually is. Consider something humble: a hallway, long, narrow, and familiar. If the hallway is straight, it has two ends. Walk far enough in either direction, and you reach a wall. But now imagine a hallway that curves and connects back onto itself, a circular corridor. You can walk forever and never encounter an end. The hallway is finite, its length is fixed, and yet there is no edge. Nothing mystical has happened. We have simply changed the way space is connected. This is not a metaphor pulled out of thin air. It is a precise illustration of how finiteness and boundary are not the same thing. The hallway contains only so much space. You could measure its total length, but there is no privileged location where the hallway stops, no place where the rules change, and once you accept that such a structure is possible in one dimension, the leap to higher dimensions becomes less threatening. The surface of a cylinder, for example, can be finite in one direction and infinite in another, yet still have no edges in the curved direction. The surface of a sphere is finite in area, yet completely edge-free. Walk long enough, and you return. No cliffs, no walls, just continuity. What unsettles us about applying this idea to the universe is not logic. It is scale. We are comfortable with curved surfaces we can see. We are uneasy when curvature becomes the architecture of everything. But the universe has been preparing us for this discomfort all along. We have already seen that space can curve, that geometry can be non-Euclidean, that topology can allow paths to reconnect, that expansion can create horizons without walls, That quantum structure can erase the very idea of a continuous background. And now, all of these threads come together here, at the apparent paradox. A universe can be finite because it contains a finite amount of space. It can be edgeless because that space is connected in such a way that there is no boundary. The contradiction dissolves, and there is something deeply revealing about how long it took humanity to accept this. Not because the idea is obscure, but because it challenges a deeply emotional expectation. We want an end. We want a place where the question stops, where curiosity can rest. An edge gives closure. An edgeless universe does not. It tells us that you can keep going, not toward a final answer, but through an endless continuity of structure. It tells us that the universe does not end with a punctuation mark. It simply keeps unfolding. This realization also reframes what it means for the universe to be complete. Completeness does not require enclosure. A book can be complete without being bound in leather. A melody can be complete without a final chord that resolves everything neatly. Completion, in this sense, is about coherence, not containment. The universe appears to be coherent without walls, and this has practical implications as well. If the universe were finite with an edge, that edge would introduce new physics, boundary conditions, special rules, something that distinguishes the last place from all others. But no such distinction has ever been observed. Everywhere we look, the laws of physics appear the same. There is no hint of a cosmic corner. This uniformity is powerful evidence. It suggests that there is no special place where the universe transitions from something to nothing. No seam where existence is stitched shut. And notice how often the edge has retreated as our understanding deepened. First, it was the edge of the earth, then the edge of the sky, then the edge of the galaxy, then the edge of the observable universe. Each time what felt like a boundary turned out to be a limit of perspective, not of reality. The paradox of a finite yet edgeless universe fits this pattern perfectly. The edge dissolves when we stop insisting that space behave like a container. There is also a quieter philosophical shift embedded here. If the universe has no edge, then existence does not need justification beyond itself. There is no outside that must be explained, no backdrop against which reality is staged. The universe is not something placed somewhere. It is the place. That idea is unsettling because it removes a layer of explanation we have grown used to. We often ask what lies beyond, but here the answer is simply that beyond does not apply. And this is not a failure of imagination. It is an expansion of it. A finite but edgeless universe invites us to think of reality not as a box, but as a self-contained structure, one that holds itself together through geometry and connectivity, not through walls. And there is something profoundly elegant about that. The universe does not need to be fenced in to exist. It does not need a boundary to be whole. It is whole by virtue of its internal consistency. This also resolves a lingering tension between mathematics and experience. Mathematically, there is no contradiction in a finite, edgeless space. Experientially, we struggle because we cannot picture it easily. But the universe is not obligated to be easily pictured. It is obligated only to be what it is. And so the paradox that once felt like an obstacle becomes a bridge. It connects everything we have explored so far: curved geometry, global topology, expanding spacetime, horizons without walls, quantum structure without background. All of them point toward the same conclusion. The universe can be finite without ending. And that realization carries a strange emotional resonance. It suggests that the universe is not a place you could ever fully reach the end of, not because it is infinite in the naive sense, but because it does not present itself as something that ends at all. There is no final destination, no cosmic edge to touch and turn back from, only continuity. And yet, this does not mean that science throws up its hands. On the contrary, this understanding sharpens the final question. If the universe has no edge, if finiteness does not imply a boundary, then what finally is the best answer science can give to the original human question. Not a metaphor, not a comfort, but a clear statement, grounded in everything we have learned. And so, having untied the paradox, having seen how something can be limited yet unbounded, we are now ready for that final synthesis, the moment where all the strands come together, not to close the story, but to state as clearly as we can what modern science actually says about the edge of the universe, and why that answer, far from ending our curiosity, leaves it more open than ever. And so, after this long and patient journey, after circling geometry, expansion, topology, quantum structure, and the quiet erasure of every wall we once imagined, we arrive at the clearest answer modern science can offer. Not a dramatic revelation, not a single equation carved in stone, but a convergence, a harmony of evidence pointing, again and again, toward the same quiet conclusion. The universe has no edge. This answer does not come from one observation alone, nor from one clever idea. It emerges because every attempt to place an edge into the cosmos creates more problems than it solves, and every attempt to remove that edge, to let space be what the data suggest it is, brings coherence instead. Let's sit with that for a moment. The universe has no edge, not because we have failed to find one, but because the concept itself no longer fits the way reality behaves. There is no outside waiting to receive the universe. There is no larger emptiness into which it expands. There is no boundary where space stops and something else begins. The universe is not an object inside something else. It is the totality of space and time themselves. When scientists say the universe has no edge, they are not making a metaphysical claim. They are summarizing what the evidence demands. Space can curve, and curved spaces do not require boundaries. Space can connect back onto itself, and connected spaces can be finite without ending. Space can expand, and expansion creates horizons without walls. Space can be quantum in nature, emerging from relations rather than extending across a background. None of these features require an edge. All of them resist it. Everywhere we look, the laws of physics appear the same. There is no direction in which they weaken, no region where geometry behaves differently, no signal in ancient light that suggests reflection or termination. The universe is astonishingly democratic. No special places, no cosmic corners. And this uniformity is one of the strongest arguments of all. An edge would be special. It would impose conditions. It would break symmetry. It would leave fingerprints. But the cosmos appears to be indifferent to location. The same rules apply here as they do billions of light years away. The distinction between the observable universe and the universe itself is crucial here. We are surrounded by a horizon, yes, a limit beyond which light has not had time to reach us. But that horizon is not a boundary of space. It is a boundary of information, a consequence of the finite age of the universe and the finite speed at which signals travel. Confusing that horizon with an edge is understandable. It feels like an enclosure. It feels final, but it is not. Beyond it, space continues. Galaxies exist. Physics unfolds. Reality does not end simply because we cannot see it. And that realization carries a subtle humility. The universe does not arrange itself to be fully visible from any one point. There is no privileged vantage. Every observer has their own horizon. And yet, none of them mark the end of existence. Geometry reinforces this. The universe may be flat on the largest scales, or gently curved. It may be finite or infinite, but in all cases consistent with observation, it remains unbounded. Whether space stretches forever or closes softly upon itself, there is no edge to encounter. Topology deepens the picture further. Space may connect in ways that defy intuition. Paths may loop, regions may repeat, or they may not. But again, no boundary is required. Connectivity replaces confinement. Dark energy strengthens the conclusion. It spreads uniformly. It accelerates expansion. It smooths rather than sharpens. It does not gather at rims or create cosmic shorelines. It treats space as something that continues, not something that ends. Quantum theories push the idea to its limit. At the smallest scales, space itself may not be fundamental. If space emerges from deeper relations, then edges become artifacts of description, not features of reality. Boundaries belong to models, not to the universe. And when scientists test these ideas in simulations, the verdict becomes practical as well as philosophical. Universes without edges match what we observe. Universes with edges do not. They distort patterns. They introduce anomalies. They complicate what is otherwise elegantly explained. So the final answer of science today is not that we have looked far enough and found nothing. It is that every layer of understanding we add makes the idea of an edge less necessary and less coherent. The universe has no edge because there is no outside to define one. Because space itself can curve and close without ending. Because horizons are not walls. Because energy fills space uniformly. Because quantum structure does not tolerate termination. Because the data simply do not support it. And yet, this answer is not a conclusion in the emotional sense. It does not close the story. In fact, it opens it wider. A universe without an edge means there is no final place to reach, no ultimate boundary where exploration stops. It means the cosmos is not a box to be mapped, but a structure to be understood. A continuous fabric whose depth is not measured by distance alone, but by insight. This reframes curiosity itself. The question is no longer where does the universe end? It becomes how does it behave? How is it shaped? How does it connect? How did it begin? How will it evolve? And what deeper layers of structure remain hidden beneath what we currently understand? There is also something quietly comforting about this picture. The absence of an edge means the universe is not fragile. It does not rely on a boundary to hold it together. It is self-consistent, self-contained, held together by its own rules. And, perhaps there is a lesson here that extends beyond cosmology. We search for edges because we are finite creatures. We look for endings because they give us a sense of completion. But the universe does not offer that kind of closure. It offers continuity instead. Time is not a clock ticking toward a final moment. It is a dimension unfolding. Space is not a room waiting to be filled. It is a geometry expressing itself. Reality is not framed by walls. It is woven from relationships. In this sense, the universe without an edge is not a cold, indifferent place. It is an invitation to keep asking questions that do not resolve neatly, to accept that some mysteries deepen rather than conclude, to find meaning not in final answers, but in ongoing understanding. And so, the final answer of science, as it stands today, is both simple and profound. The cosmos has no edge, not because it is infinite in the naive sense, not because it hides its boundary from us, but because the idea of an edge no longer belongs to the way reality is structured. The universe is not a thing with sides. It is a continuous space-time process, a fabric without seams, a story without a final page. And perhaps that is why, even after all this careful reasoning, all this data, all this quiet confidence, the universe still feels endlessly fascinating. Because in a cosmos without edges, exploration itself has no natural stopping point. There is always another question waiting just beyond the last answer, another layer of structure, another way of seeing. And that, I suppose, is the most honest conclusion science can offer. Not an ending, but an opening. A reminder that the universe does not end in a wall, and neither does our curiosity. It simply carries on, inviting us to listen, to wonder, and to keep going, wherever the next question leads. And so, having accepted that the universe has no edge, having followed the evidence until the very idea of a boundary dissolves, we find ourselves in a curious position. The original question that set this journey in motion has been answered, and yet the sense of wonder has not diminished. In fact, it has grown deeper, because when the universe has no edge, the story does not conclude. It opens outward, inviting us to ask questions that no longer revolve around where reality ends, but around how far reality can extend in meaning, structure, and possibility. You see, an edgeless universe subtly changes the role of humanity within it. When people once imagined a universe with a boundary, there was comfort in the idea of limits. A finite cosmos felt graspable, even conquerable. You could imagine mapping it, reaching its end, standing at the final shore and looking back. But a universe without an edge refuses that closure. It denies us the satisfaction of finality. And that's the thing. It replaces it with something far richer. If the universe has no edge, then exploration is no longer about arrival. It is about relationship, about understanding how different parts of reality connect, influence one another, and emerge from deeper principles. The absence of an edge means that every new discovery does not bring us closer to the end, but deeper into the fabric itself. And this has profound consequences for how science now frames its most ambitious questions. Instead of asking where the universe stops, we ask whether the universe might have more dimensions than the ones we perceive. Not as distant places to travel to, but as hidden directions woven into space-time itself. If space has no edge, then it may also have more depth than our senses can access. Dimensions curled so tightly that they escape direct detection, yet influence the behavior of matter and energy in subtle ways. In such ideas, the universe does not expand outward into emptiness. It unfolds inward into complexity. The absence of an edge also reshapes how we think about the possibility of other universes. The idea of a multiverse often sounds extravagant, even reckless. But notice how it emerges naturally once the universe is no longer treated as a container with walls. If space and time form a continuous structure with no boundary, then it becomes meaningful to ask whether our observable universe is only one region within a larger cosmic pattern. Not separated by edges, but by different physical conditions, different histories, different ways in which space and time can organize themselves. And here again, the lesson repeats. These other regions would not lie beyond an edge. They would not exist outside our universe in the everyday sense. They would be part of a broader structure that does not lend itself to simple inside and outside distinctions. And what is striking is how often the absence of an edge returns as a stabilizing principle. Even the boldest modern theories, when taken seriously, tend to avoid hard boundaries. They replace them with transitions, with emergent behavior, with limits of observation, rather than limits of existence. There is also a quieter implication, one that touches something deeply human. A universe without an edge suggests that meaning is not found at endpoints. It is found in patterns, in processes, in the way complexity arises from simplicity, again and again, without ever exhausting the possibilities. Stars form and die. Galaxies collide and reshape themselves. Space expands, horizons shift, structures dissolve and reappear in new forms. And through all of this, there is no final destination, no ultimate frame where the universe pauses and declares itself complete. And perhaps that is why the idea of an edgeless universe feels, at first, unsettling. We are creatures who tell stories with beginnings, middles, and ends. We look for arcs, for closure, for conclusions. But the universe does not tell stories that way. It tells stories that branch, that loop, that deepen. Time itself reflects this. It does not march toward a cosmic wall. It unfolds, carrying change forward without promising a final scene. Even the ultimate fate of the universe, whether it cools endlessly, transforms through unknown processes, or evolves into something unrecognizable, does not imply an edge. It implies transformation. And transformation is a very different thing from termination. There is also a subtle ethical resonance here. When the universe has no edge, no final boundary, no ultimate vantage point, humility becomes unavoidable. No single perspective captures the whole. No observer occupies a privileged position. We are participants, not spectators standing outside the frame. The cosmos does not revolve around us, but neither does it exclude us. We are patterns within a larger pattern, made of the same ingredients, governed by the same rules. The atoms in our bodies were shaped in stars. The space between our thoughts is governed by the same geometry that governs the space between galaxies, and that realization softens the coldness that some people associate with modern cosmology. An edgeless universe is not an indifferent void. It is a continuous structure that includes us completely. There is no outside from which we are excluded. Even ignorance takes on a different character here. There will always be things we cannot know, not because the universe hides them behind walls, but because knowledge itself is bounded by perspective, by causality, by the finite nature of any observer. Mystery is not a flaw in the universe. It is a feature of being inside something without edges. And, that may be the most profound shift of all. We stop imagining ourselves as explorers heading toward a final frontier and begin to understand ourselves as listeners, interpreting echoes within an endless structure. This also reshapes how we think about the future of science. If there is no edge to reach, progress is not measured by how far we have gone, but by how deeply we understand. The next revolutions will not come from traveling farther outward, but from seeing familiar phenomena in new ways, from uncovering hidden connections, from realizing that concepts we once thought fundamental are emergent, approximate, and context-dependent. Space, time, matter, energy. Even causality itself may turn out to be expressions of something deeper. And in such a framework, edges would not just be absent, they would be meaningless. And that's the thing. The absence of an edge is not a statement about emptiness. It is a statement about richness. A universe that ends is simple. A universe that does not end must explain itself through structure alone. And so, as this chapter unfolds, we find ourselves no longer searching for borders, but for coherence, for principles that explain why reality is the way it is, without appealing to what lies beyond. The universe has no edge, and because of that, it does not offer us the comfort of final answers, but it offers something better. A continuous invitation to explore, to question, to rethink what we thought we understood. And perhaps in the quiet moments, when we look up at the night sky and feel that familiar mixture of smallness and awe, we can sense it. Not a wall, not a boundary, but an openness. A vastness that does not end, not because it stretches forever in a straight line, but because it curves, connects, evolves, and deepens without ever running out of reality. And so the story continues, not toward an edge, but onward into understanding. And so, without ever striking a wall or reaching a final shore, we find ourselves at a moment of reflection rather than arrival, not because the journey has ended, but because the question that began, it has changed us along the way. We set out asking whether the universe has an edge, imagining some distant place where space itself might stop. What we have discovered instead is something far more subtle and far more beautiful. The universe does not deny us an edge out of secrecy or distance. It denies us an edge because the idea itself does not belong to the way reality is built. And that's the thing. This realization is not merely a technical result of physics. It is a shift in perspective, one that quietly echoes through how we think about existence, knowledge, and our place within the cosmos. For most of human history, edges felt necessary. They gave comfort. They gave orientation. To know where something ends is to feel that it can be understood, contained, mastered. We built walls around cities, borders around nations, frames around pictures, and we carried that habit of thought upward into the sky. Surely the universe, too, must have a frame. Surely it must end somewhere. But science, patiently and without drama, has taught us otherwise. Every layer of understanding has peeled away another imagined boundary. The edge of the earth gave way to curvature. The edge of the sky gave way to depth. The edge of the galaxy gave way to countless others. The edge of the observable universe revealed itself not as a wall, but as a horizon shaped by time and light. And at each step, what felt like an ending turned out to be a limit of perspective, not a limit of reality. This pattern matters. It tells us something about the relationship between human intuition and the universe we inhabit. Our instincts are not wrong. They are incomplete. They evolved to help us survive on a small planet, under a modest sky, moving slowly through space and time. They were never meant to grasp the architecture of spacetime itself. So when intuition insists that finiteness must imply an edge, science gently disagrees. When intuition demands an outside, science replies that outside is not required. When intuition seeks a final boundary, science offers continuity instead. And this does not diminish the universe. It enlarges it. A universe without an edge is not vague or undefined. On the contrary, it is precisely structured. Its behavior is governed by geometry, topology, causality, and energy. These are not abstract ideas floating above reality. They are the rules by which reality unfolds. Space curves rather than ending. Expansion creates horizons rather than walls. Connectivity replaces confinement. Quantum structure dissolves the background altogether. And through all of this, the universe remains whole, complete, and self-consistent. What is perhaps most striking is how consistent this picture is across scales. From the largest structures traced by galaxies to the smallest hints of quantum spacetime, the universe resists termination. It does not favor special locations. It does not break its own rules at imagined borders. It does not announce an end. Instead, it invites understanding through relationships, and this changes how we think about knowledge itself. If there is no edge to reach, then knowing the universe is not about getting to the end of a map. It is about learning how the map is drawn, how its symbols relate, how its patterns repeat and transform. Knowledge becomes depth rather than distance. There is a quiet humility embedded in this. No matter how far science progresses, there will always be horizons, not because the universe is hiding something behind a wall, but because being inside a universe without edges means there is no position from which the whole can be seen at once. Every observer is local, every perspective is partial, and yet those partial perspectives overlap. They connect. They allow us to build a coherent picture, piece by piece, not by standing outside the universe, but by understanding how its internal logic works. This is perhaps the deepest lesson of all. The universe does not require an external vantage point to be understood. It can be known from within, through patterns, symmetries, and consistency. And there is something profoundly human about that. We, too, are finite and yet unbounded in a certain sense. Our lives are limited in time, yet our ideas can circle back, connect, deepen. We do not need an edge to be meaningful. We need coherence. The edgeless universe mirrors this truth. It tells us that meaning is not found at endpoints, but in structure. That completion does not require closure. That wholeness can exist without finality. This does not mean that every mystery is solved. Far from it. Questions remain about the origin of the universe, about the nature of dark energy, about the quantum foundations of spacetime, about whether reality includes dimensions or regions beyond our current theories. But notice how these questions differ from the one we began with. They are not questions about where reality stops. They are questions about how reality works. And that shift is everything. When we stop searching for edges, we begin searching for principles. When we stop asking what lies beyond, we ask what lies beneath. And that is where discovery truly begins. There is also a subtle, emotional transformation that accompanies this understanding. An edgeless universe can feel unsettling at first. It denies us a final reference point. It removes the comfort of imagining a cosmic boundary that defines everything else. But if we sit with it long enough, something else emerges. A sense of openness that is not empty, but rich. The universe is not an unfinished object waiting for its border. It is a finished structure that does not need one. And perhaps that is why the night sky feels the way it does. Not like a ceiling, not like a wall, but like an opening. a depth that draws the mind outward, not toward an end, but toward connection. When we look up, we are not staring at the inside of a container. We are looking into a geometry that includes us completely. There is no place we are excluded from by an edge. We are inside the universe in the deepest possible sense. This realization also reshapes how we think about the future. Exploration will continue. Telescopes will see farther. Experiments will probe deeper. Theories will evolve. But there will never come a moment when we declare that the universe has been fully mapped because we have reached its boundary. Progress will be measured not by how much space we have covered, but by how much understanding we have gained. And that is a far more sustainable form of curiosity. An edgeless universe ensures that wonder does not run out. And so, as this long reflection gently settles, we can say this with confidence and with a certain quiet awe. The universe does not end, not because it is infinite in the simple sense, but because it is structured in a way that does not require an ending. There is no cosmic wall waiting to be found, no final horizon that marks the edge of existence itself. Only horizons of knowledge, always shifting, always inviting us forward. And perhaps that is the most fitting conclusion of all. A universe without edges is a universe that refuses to close the book. It leaves the story open, not unfinished, but alive. Alive with questions, connections, and possibilities that extend as far as understanding itself can reach. And so we do not stand at the end, we stand within, listening, wondering, and moving on, not toward an edge, but deeper into the quiet, endless structure of reality.